This chapter is titled Spontaneity, Entropy, and Free Energy. It's actually a continuation of our previous discussions on thermodynamics, which is thermo is heat, dynamics is how does it move. What we're going to focus on in this chapter is spontaneity of reactions. What makes a reaction go from reactants to products? And we've talked about that in the past in terms of if the reactants are higher energy than the products, you tend to get the reaction to go. But we can still get reactions going when the products are higher energy than the reactants. So it's kind of hard to explain that with energy alone. So let's go to this diagram where we have, I think we've used this before, energy, and this is progress of the reaction. And in our example, we've got an exothermic reaction. We start off with energy for the reactants here. Then we have to go through a transition state where we add energy. Yeah, we did discuss this in kinetics. And then you end up with products at lower energy. But we know that the difference between this place here and this here is our enthalpy. And it's a negative enthalpy because products have less energy than the reactants, and it's exothermic. When we talk about kinetics, we're dealing with this part of the diagram. This is what determines how fast the reaction goes. How much energy does it take to get over that hump? When we talk about thermodynamics, we want this part and this part. So this is thermodynamics and that side too. So what that means is we only care about where it starts and where it ends. It doesn't matter what happens in between. Illustrate this point. Diamond is kinetically stable. In other words, you got a diamond. My wife has a diamond on her ring finger, and it's going to be there just like that for essentially forever, like for thousands and thousands and thousands of years. Right? It's kinetically stable. It's not going to, nothing's going to happen to it in 100 lifetimes. But thermodynamically speaking, it is unstable. In other words, if you wait long enough in an oxidizing atmosphere, like in air, that diamond will eventually turn into carbon dioxide. So you have two approaches there, the kinetic and the thermodynamic. The kinetic discussion is determined by the path. In other words, if your reaction proceeds through without a catalyst, we talked about that. Without a catalyst, it goes through one path, one mechanism. If it has a catalyst, then it goes through a different mechanism, which allows it to go faster. So for kinetics, this is called a path function. In other words, the path that it takes determines the outcome speed. Whereas thermodynamics is a state function. In other words, we only care about where it starts and where it ends. It doesn't matter how it got there. It's like let's see, how much energy does it take to get from Charleston to Beckley? Right. Well, your potential energy at the level of Charleston changes as you go up to Beckley by about 1,000 feet. So you have more potential energy when you get to this plateau. How much energy does it take to get there? It depends on the path. If you take a direct route, it'll take a certain amount of energy. If you take the winding roads, it'll take probably more energy. Like if you go through, I forgot the name of the town now, where WVU Tech used to be. Montgomery, thank you. If you go along the river to Montgomery and then back up toward Oak Hill and then back around, it'll take more energy to get to Beckley that way. But you're at the same height. So it's the difference between the path function and the state function. Thermodynamics is a state discussion. Now, there are certain parts of thermodynamics where we introduce path into it, but in general, thermodynamics refers to state functions. When we talk about spontaneous process, we mean a process, and it doesn't have to be chemical, be physical or chemical, a process that proceeds without any outside intervention. In other words, and we know that if our windows are not insulated, which used to be common, then you're going to get heat transfer. In the summer, you're going to get heat transfer into your house. Or in the winter, you're going to lose heat to the environment. We still do that, but it's not quite as bad as it used to be. That's a spontaneous process. We always know that heat goes from high temperature to low temperature. But there are some processes that occur spontaneously, and we can't explain them by what we know up to this point. All right, but we're going to talk about that in just a minute. Let's take this as an example. Most chemical reactions have a difference in energy of the reactants and products, right? There are very few, and I couldn't find an example. I looked everywhere. Find an example where the reactants and products have exactly the same energy. Right? They can be very close. So I have to use a physical example rather than a chemical example. What if you have 2.4 moles of gas in a 4-liter bulb at a temperature of 32 degrees? So we got a 4-liter bulb, 4-liter bulb, and we have 2.4 moles of gas in it. This is gas, and it's at 32 degrees, all right? And it's connected through a valve to a 20-liter bulb. And so we got a valve here, and it's connected to a bigger bulb, 20 liters. But this is a vacuum. Okay. And the temperature is constant for everything. The temperature does not change. So we can't explain anything that happens based upon a difference in temperature, because the temperature is 32 degrees and it doesn't change. All right, so what happens when you open that valve? We intuitively, we know what happens, right? The air goes, that gas goes in there until it equilibrates. Okay, so how do you explain that? There's no driving force in terms of energy because the temperature is the constant. Right? So we need another way to explain it. And before we do that, we need to review some terms and define some terms. Let's start with delta E. I know what delta H is first, but let's start with delta E. This is internal energy. Internal energy. Sometimes in textbooks, you'll see this as U rather than E. I think they choose U because E is often used for something else. But for this discussion, we're going to say delta E is internal energy. And this is the sum total of all the energy in the system in terms of kinetic energy and potential energy. Okay. All the energy that we can account for is this internal energy. Now for delta H, this is enthalpy. And this is internal energy plus whatever work can be done. So enthalpy is going to be internal energy plus actually it's delta P V. We only pull P out and put the delta over here when P is constant. Maybe I better do that. Right, be consistent with the slides. So it's P delta V. And this references the work that we can do with the gas. Have we talked about that yet? We haven't done that yet, have we? Okay, maybe that's coming in another slide. Okay, enthalpy refers to the heat change in a reaction or in a process, right? And this is viewed in terms of potential. What's the potential heat energy available? Whereas Q is actual heat flow. So if we had a difference in temperature, we would see heat flow from the high temperature to the low temperature, and we could measure it. Okay. In fact, we did that, didn't we? With calorimetry. Yeah, we did measure that. And then W is work. Right? And work is still defined as force times distance. Force applied through a distance gives you work. Also in terms of gas, changes in gas volume and pressure is P delta V is also another way to measure work. Okay, so now that we've defined those terms, let's see what we can do with them. All right, let's look at each one of these in terms of what has just happened here. Right, let's start from the bottom. Was there any work done? There was probably a pressure change, right? We had gas confined in here, and Boyle says if the volume increases, the pressure decreases, right? But was it working against, was that change in pressure working against, let's see. Well, now I've got to look at it this way, because we did change pressure. But as the pressure went down, the volume went up. So it's a wash. Nothing happened. No work was done because there was no force applied through a distance against some resistance. That's what I'm trying to say. Right? If we had an expanding gas against an external pressure, like in a piston with a cylinder, and we've got maybe a kilogram weight on it, and then the gas expanded against that force, then work would be done. But in this case, no work was done. It's not working against any external forces, right? So the work in this case is zero. How about heat flow? No temperature change, no heat flow. And that means with no heat flow, there's no change in enthalpy either. Did we change the internal energy? Well, if this is zero, and this is zero, right? This is zero, and that's zero, then that has to be zero. Right? So they're all zero. There's no change in any one of them. So we can't explain the process based upon what we know up to this point. Right? So we've got to, well, scientists did this. We've got to invent another way to explain it. Here's another way to explain the change in heat and change in energy. If there's no temperature change, there's been no change in energy, no change in enthalpy. And of course, that one follows from what we've already discussed. There's no work done. Okay. So what's the driving force for this process? Right? We have to come up with a new term. It's called entropy. And it's given the letter S. And usually, not usually, always, when we speak of entropy, we're speaking in terms of a change in entropy. What was it to begin with? What is it afterwards? This was introduced by Rudolf Clausius. See, do I have a picture of him? There he is. Looks like a happy fellow, doesn't he? In those days, in the late 19th century, when pictures were being taken, the photographic plates were what we call, the difference between slow and fast film, right? Fast film, you can snap a shot with just a very quick shutter. Slow film, you have to take in a lot of light to get the effect. Well, in the beginning of photography, those photographic plates were very, very slow. So your subject had to sit there very still. And that's one explanation. The other explanation may be that they didn't want anybody smiling. Or maybe he was like George Washington, had false teeth. But pictures that old, nobody ever smiles. I've seen pictures of my grandparents, right? Well, they're just stone cold. Anyway, that was Clausius, and he introduced this concept of entropy. Entropy, one easy way to explain entropy, although it's an oversimplification, is in terms of the word disorder. Now, this is not the end-all explanation for entropy, but it's a good starting place. If we look at the in terms of say a room of my teenage son, well, he's not a teenager anymore, but he still has the same room habits, right? When you go into his room, it looks like a tornado hit it. Right? That would be high entropy, lots of disorder. Well, I can't use my house as an example because the whole thing is disordered. Let's say you went into someone who's severe OCD, right? Their house is going to be extremely ordered, everything in place. Now, I will say, when my son was small, he liked Matchbox cars, and he had a whole box full of them. And before he went to school, he'd get up in the morning and he'd arrange them in a certain way in front of his closet. So that was be maximum order, right? And my wife, she was a lot healthier then, so she would do some housework, and she'd go into his room and need to get into the closet, and she'd move his cars and do her thing, and then she'd put his cars back. So that looks like exactly the way they were. He'd come home and said, and look at her and said, "You moved my cars." He knew exactly where they were to the millimeter. But that would be an ordered situation where all those cars were in a row. So when this gas expands, the driving force is an increase in entropy, an increasing disorder. That's the difference between the images. The molecules have much more space to move around, and that's what they want. An increase in entropy. So in all spontaneous processes, there must be an increase in entropy. We can speak of entropy in terms of the entire universe or in a localized part of the universe. And very often it's more useful to isolate a part of the universe. Just say, all right, this is isolated. We talked about that before, didn't we? Systems that are isolated means mass, no exchange of mass, and no exchange of energy. That's an isolated system. Like an isolated region of space. The system is going to be in here somewhere. Right? And then everything else is surroundings. I think we've talked about this before, but it bears repeating. And then when we discuss processes that occur, the processes are in the system and any exchange with the surroundings. Now, if the system is open, that is, mass and energy can pass freely between the two. If the system is closed, then mass can't transfer, but energy can. And then, of course, isolated means nothing gets across that barrier. So when we did our calorimetry, we had our calorimetry cups, and we were trying to simulate an isolated system. The calorimeter cup was isolated from the outside, so that everything that happened in Vegas stayed in Vegas. Okay, so if our delta S is greater than 0, which in this case it is, we see an increase in disorder. All right. The truth is, and the more accurate way to describe entropy is how many possible arrangements can we make out of the elements in a system. Right? So if we have, say, 10, 4, 5, 6, 7, 8, 9, 10, we have 10 particles on this side, then there are a limited number of arrangements we can have in that space. But if we open the space up here, we have a lot more possible arrangements, right? We call those microstates. So the more microstates you have, the higher the entropy. And the reason we need to talk about it in those terms is if we just consider disorder, we're only discussing physical arrangement of particles. Whereas disorder can also be discussed in terms of increases and decreases in energy, arrangements of energy in a system. So we need to migrate toward microstates away from just a general topic of disorders. So to continue with the microstate discussion, let's see, do I have any text here? Yeah, I do have text. Each configuration that we see here gives a unique arrangement of particles. So if we have 4 particles in this case, and we have a double bulb, then one possibility is that all 4 particles are on one side. That's only one microstate available. If we go the other route, if we move them all to the other side, that's only one microstate for that possibility. Right? If we move 1 to one side and leave 3 on the other side, then we have 4 possibilities. Right? So we have an increase in microstates there. If we put 2 on the left and 2 on the right, then we have a total number of microstates of 6. And then, of course, if we have 1 on the left and 3 on the right, then it's the flip side of arrangement 2, arrangement 4. So we have 4 possible microstates. The greatest number of microstates is the one where we have 2 on one side and 2 on the other, which will be roughly discussing in terms of an equalized pressure. So we can talk about entropy in terms of positions. That is, that's the physical arrangement of particles. And here we're gonna continue with this disorder analogy because it's very helpful, especially with positional entropy. If we look at a substance say, that can be a solid. It can also be a liquid and also be a gas. And we know in order to do that, we've got to add energy. And so we are adding energy to the system. So the solid is relatively ordered. In other words, all the particles are locked in place, like a sodium chloride crystal. If we heat it up high enough, we can melt it. We get liquid sodium chloride. It takes a lot of energy, but we can get there. Right? That has more disorder because you have more possible microstates. In other words, they're not locked in place. All these ions from sodium chloride can be in different places. So you get an increase in disorder. If we heat it further and make gaseous sodium chloride, then you have even more positional possibilities. Even if it's in the same volume, but it's more likely to be in a greater volume, which would also add to the number of microstates. So as you go through phases, the gas is more disordered than the liquid, and the liquid is more disordered than solid. So the entropy increases as you go from solid to liquid to gas. And that's positional probability of these states. Right? When thermodynamics is discussed, it's like quantum mechanics. It's all based on probability. Right? We don't have the computing power to follow every atom or every ion in a solution or in a gas or in a liquid, whatever the case may be. We don't have the computing power or the instrumentation to identify where all these particles are. So we have to treat it probabilistically. So it's more probable to find atoms or ions in a gaseous state in different microstates than it is in a liquid. Okay. We can discuss continuing with this topic of, well, actually we're going to migrate from positional entropy, which is intuitively, it's easier to understand what that they're referencing. When we talk about energy entropy, and this is a topic that's not covered in your textbook. I don't know why it's not there, but I think it's important. When we look at increases and decreases in energy, now we have to identify, did it happen to the system or did it happen to the surroundings? And if we have an exothermic process, then the system is increasing in energy. And if we have free energy transfer, right, it's not an open system, it's a closed system to mass transfer, but not to energy. So if energy increases in the system, some of it's going to transfer as heat into the surroundings. Right? So in an exothermic process, we're transferring heat, and that makes this a negative value. Transferring heat from the system into the surroundings. Now the total randomness, we have to look at it in terms of both positional and energy entropy, but we're going to set positional aside for the moment. Because if you go from, say, let's see, hydrogen gas plus oxygen gas makes water, right? So let's see, let me balance that. That's 2 here and 2 here. Well, we've got 2, 3. We've got 3 moles on this side and only 2 moles on that side. So for positional entropy, we've actually decreased going from here to here, right? From 3 to 2. We decreased the number of particles in that space. But it's an exothermic process, so we've increased the energy entropy. So that there has to be a balance, right? And this process we know is spontaneous. All you have to do is give it its initial activation energy and it'll go. Right? Just watch this. Some of the rockets that we're putting up in the space now are based upon liquid oxygen, liquid hydrogen to drive their engines. Now, SpaceX uses, well, for their Starship, they use methane and oxygen. And their Falcon 9s, they use kerosene and oxygen. But similar concept. Anyway, we have the possibility to look at it two different ways. But an exothermic process implies an increase in energy randomness for the surroundings. Because if an exothermic, you're increasing energy, it transfers to the surroundings, so that the energy entropy for the surroundings is going to increase. And the energy randomness for the, well, this slide only talks about the surroundings. If this system is losing energy in the process, then its energy entropy should decrease. Right? And an endothermic would just go the other direction. Okay, let's work a little intuition here. Try to get a handle on this, because the idea of entropy, intuition regarding entropy only goes so far. And then further discussion has to be mathematical, actually. We're not going to go there. Well, we're gonna go part of the way. We're gonna dip our toes in the water, right? But we're not gonna go full calculus on it. Okay. So let's see if we can predict the sign, the entropy, change in entropy for each of the following processes. Is it positive increasing or is it negative decreasing? So in this situation, we have to define what is the system, because that's what we're focused on. The evaporation of alcohol. So if you pour some alcohol on the tabletop, what's going to happen to it? It's going to evaporate, right? So the alcohol itself is increasing its entropy as it evaporates. So we should get a positive value. You don't have to know that stuff. This is just what was it? Clausius introduced the concept, and then Boltzmann actually put numbers to it. Right? So the entropy for this one is going to be positive. How about the freezing of water? It's going from a liquid to a solid. Entropy should decrease. Yeah. Compressing an ideal gas at constant temperature. Right. Yeah, it should decrease. You're giving fewer possible microstates available. Heating an ideal gas at constant pressure. If you heat the gas, you're adding energy to it. And if the pressure is constant, that means the volume is going to increase. Because Charles' law says you increase the temperature, you increase the volume. So we're actually increasing both positional and energy entropy at the same time. You dissolve sodium chloride in water. Starts out as a solid, right? Now it's going into solution. It's got more space, more possible microstates. It should increase. Okay. So that was a little exercise in intuition. All right. Remember the first law of thermodynamics. Let's see. We'll put a heading up here. The first law of thermodynamics says that the total energy content of the universe is zero. In other words, you can't add energy, you can't take energy away from the entire universe. Okay. That's one way of expressing it. The second law is where we find a discussion of entropy. In a spontaneous process, there's always an increase in entropy of the universe. In other words, the change in entropy for the universe is always greater than zero. When you talk about the entire universe, when we isolate our system and surroundings, you can get a decrease in entropy, an overall decrease in entropy. But for the entire universe, entropy is always increasing. Right. So the popular way to express that is that the universe is running down. Right. Eventually, and that fits with some theoretical astrophysicists saying that the universe is going to go out with a whimper. It's just going to keep expanding until it gets cold, absolute zero, and that's the end of everything. There are others that say it's going to get up, expand to a certain point, and then the gravity of the universe is going to contract it. And it's going to go from a big bang to a big crunch. So who knows, right? That's billions and billions and billions of years in the future if we make it that far. Okay. Now what we're going to do, the textbook very often uses a subscript of universe for entropy when they actually mean isolated system surroundings. Right? So I'm going to make a distinction there. If I write a delta S with no subscript, then we're talking about this situation. Only when I write universe down here do I actually mean the entire universe. And you can also subscript it with SYS for system or SUR for surroundings, because we can talk about change in entropy for either one and how they relate to one another. All right. That's the first law. Total energy is increasing. So your textbook puts it this way, and I think it's better this way. The delta S total, the change in entropy for this situation is equal to the change in entropy for the system plus the change in entropy for the surroundings. So in this case, delta S can be negative or positive. And what we're going to find out, that may be on the next slide. Let me see. What we're going to find out is that when this value is positive, then we can say whatever happens in here is spontaneous. When it's negative, it's non-spontaneous. Okay. And processes that go in one direction spontaneous are non-spontaneous in the reverse direction. Now, if the delta S total is zero, that means it's all at equilibrium. There's no driving force to make it go one way or the other. Now, our discussion of equilibrium also says that that doesn't mean things are frozen in space. It just means that the rates one direction are equal to the rates the other direction. That's what equilibrium means. But in terms of entropy, right, if we're at equilibrium, then there's no change in entropy, no matter what's going on. Is anybody confused yet? No, good. That's a good sign. Because entropy has a tendency to twist your heads around. Okay, for this process where we're going from some substance in liquid form to solid form, an increase, which direction is an increase in energy randomness or energy entropy? Let's put it up here. Let's see. We're going, something is going from liquid, right? Yeah, going from liquid to solid. If we're talking about energy randomness, it takes energy to go from solid to liquid. You have to put energy in. So if we're going to actually, which direction involves an increase? An increase in energy entropy would be this direction. Energy entropy would be this direction, because we have to put energy into the solid to make it a liquid. How about an increase in positional? Well, that's the same. Positional should be the same. Right? Because we're giving it more microstates going from solid to liquid. Now, let's see if they're going to make a liar out of me. Liquid to solid is exothermic, so energy randomness favors the formation of the solid, decreasing from liquid to solid. Decreases that way, so it increases the other way. Yep. Positional randomness decreases from liquid to solid, so its increase of both of them should be to the left. Now, that's a qualitative description. The values that are actually assigned to the delta S, and we can put numbers to this, the values that are assigned will determine the total delta S for this transition. Because energy may be one, it may be a certain value this way and a different value this way for positional, and then you have to reconcile the two. And in some systems, energy entropy increases one degree way and positional entropy increases the other way. And then reconciling them determines what's the total, determines which way is favored. But in our case, they both go the same direction, so that's not a problem. What's a balance between the two types? Okay, as temperature, let's see, increases or decreases, which takes precedence? Okay. As temperature increases, positional randomness dominates. So if we take the system, this transitional system, and we increase the temperature, which one of these is more important? Well, as you increase the temperature, think of this in terms of percentage change. Right? As you increase the temperature, a 1 degree change in temperature on a percentage basis makes it's less impact. Higher temperatures, like if we were at 10 degrees, then a 1 degree change would be a 10% change. If we were at 100 degrees, a 1 degree change would only be a 1% change. Right? It's like if let's see, you're a pauper, you make you're a poor student, you're making maybe $10,000 a year, and you're independently wealthy, and you're going to school because you thought it'd be fun. So you've got several $1 million, and I say, okay, I'm going to give you $10. No, I'm going to give you $100. Let's see, be generous. Give you $100, you can right. You lose that much out of your pocket in a day, just in change. Right? I give you $100, it has a great impact on your ability to provide for you and your family. Right? That's the idea. So high temperature, the energy entropy has less impact, but positional energy has a great impact, because at high temperature, you got lots of motion, lots of microstates available. Okay. So as temperature increases, positional randomness dominates. Yeah. As temperature decreases, energy randomness is now favored, because a change in temperature has more impact on the energy input and release from a system. Okay. So at what temperature is there a balance between energy randomness and positional randomness? I might as well just state this as a fact. At equilibrium. When you're at equilibrium, melting point or boiling point, you have a balance between positional and energy entropy. Phase change, that's a better term. What if we try to apply these to other things? Describe the following as spontaneous, non-spontaneous, or you can't tell. Say that a reaction is exothermic and becomes more positionally random. It's exothermic, that means it's losing energy. So its energy randomness is decreasing and its positional randomness is increasing. Let me see. If it's exothermic, I don't get that. At one time I did. For some reason, it's not making sense to me now. Exothermic and becomes more positionally random. So instead of our hydrogen-oxygen analogy, say we've got something that produces more. Let's try something like this. Say into O4 gas is in equilibrium with 2NO2. So I'm not sure if this is exothermic or endothermic. It's probably endothermic, but this gives you more positional randomness as you go from this side to this side. That would be an increase in positional randomness, but it's probably not exothermic though. So that's a bad example. Oh, nitroglycerin. Right. When nitroglycerin decomposes spontaneously, it produces, I think we counted one time, it's like 29 moles of gas from a couple of moles of nitroglycerin. Right. We know that's exothermic, and it's also increased positional randomness. So that's definitely spontaneous. If it's exothermic and less positionally randomness, we can't tell, right? Because we don't know the balance between the two. And also, if it's endothermic and more positionally random, we can't tell that one either. But if it's endothermic and less positionally random, then we can say that one is not spontaneous in the forward direction. And A and D are not affected by temperature. And B and C, we don't have enough information. We're going to get to a more complete discussion of this when we get to free energy. That's coming. So let's look at the entropy change of the surroundings and focus on the surroundings, and that will help us draw conclusions about the system itself. If we know what's happening in the surroundings, we can imply certain things in the system. The sign of the delta S, of course, depends on the direction of heat flow. As heat leaves the system into the surroundings, then the randomness in the surroundings increases, and the process itself is exothermic. So we're transferring energy into the surroundings, making them more random. We're increasing the entropy of the surroundings. If the heat goes from the surroundings to the system for an endothermic process, then we're decreasing the randomness of the surroundings. And the magnitude of this change is dependent upon temperature. Right? So here's where we're headed with this. The change in entropy has a greater effect on the surroundings when it starts at a lower entropy than if it starts at a greater entropy. Right? It's just a percentage comparison. So another way to say that is the change in entropy for the surroundings is proportional to, that's what that sign means, to the heat transferred to the value of Q, but it's inversely proportional to the value of temperature. And this Q is intrinsically a change, because you can't measure Q unless heat has moved from high temperature to low temperature. So Q is intrinsically delta. But the T, of course, has to be identified as a change in temperature. So we're saying that that's what this is. Change in entropy of the surroundings is equal to, well, it's proportional to, I think we have to introduce a sign change. Let's see. Yeah, we have to introduce a sign change. Simply because change in entropy for the surroundings is, well, everything's relative to the system. So if Q is leaving the system, it's negative. If it's entering the system, it's positive. Same for the delta S. So the delta S relative to the system leaving would be negative and would be positive if it's increasing in the system. So if we're talking about the surroundings, we have to flip everything, right? Because these are in terms of the system only. So we have to introduce a negative sign. And we can, since delta S is a state function, then we can also equate it to delta H. Excuse me, yeah, delta H over temperature. Actually, I didn't need that. It just depends on what the temperature is. So temperature is constant. Well, not constant, but it's not a change in temperature we're interested in. I'm sorry about that. We just want the temperature. And the temperature has to be in K, of course. All right, so we have our first formula. Well, actually, we had a formula prior to that, right? Total delta S total equals delta S surroundings plus delta S system. So maybe I'll write those over here. Formulas we've done so far. Delta S total equals delta S system plus delta S surroundings, in addition to the definitions. Right? We haven't done this one yet. Actually, what is delta E? We've done this one, which is delta E plus P delta V. We're going to get to that one in a minute. We just said it's the total kinetic and potential energy, but that's difficult to quantify. Okay, and now we've got this one. So the delta S for the surroundings is equal to negative delta H over T, or if we measure a Q, it's negative Q over T. So those are the formulas we've gotten so far. And we're going to pick up where we left off in the classroom. Now you're in my office at home. And we're going to continue. We had just established that the change in entropy of the surroundings is proportional to the change in enthalpy and directly proportional and inversely proportional to the temperature. So that just means that as the temperature goes up, the change in entropy of the surroundings, well, should go down, but we've introduced a negative sign. So the negative sign is there to compensate for our convention for system and surroundings. Right? Everything is relative to the system. So if the entropy of the system, or the enthalpy, let's say, the enthalpy of the system is negative, that is, it's exothermic, we have a negative enthalpy, then we're increasing the energy enthalpy, the energy entropy of the surroundings. So in order to make this positive, we have to introduce that negative sign. All right. So we've got that formula available to us. And let's see, let me try something else. Now, that's better. Put this over here. Okay. In fact, I think I need a better marker. No, I'll just pull out a couple of them. There we go. All right. So now that we know how to calculate the entropy change of the surroundings based upon the enthalpy of the reaction that's occurring in the system, and it's also dependent upon the inverse of the temperature, then I want to digress for a moment. Enthalpy and Q, heat transfer, are essentially two different concepts. They're related sometimes, but they're not the same. Q is what we measure in the lab in our calorimetry experiment. Delta H is an expression of heat potential for any process, right? So we're actually saying that they're completely different values. Right, enthalpy is a thermodynamic potential, much like internal energy. It's a measure of the potential energy of the system. And it's defined by the following equation. Delta H equals the internal energy plus any change of pressure times volume. And pressure times volume is an expression of work that's done by a gas or upon the gas. So if we insert the equivalence of delta E, and that's one equation that I failed to give you earlier. Delta E for a system can change, but it can only change based upon two measurable quantities. One is the heat change of the system. A measurable heat change of the system will change the internal energy. And the other is any work that's done by the system or any work that's done upon the system. And so heat change, if heat leaves the system, then it's negative. If it's added to the system, it's positive. Same for work. If heat leaves this, if the work is done by the system on its surroundings, then it's negative. And if work is done on the system by the surroundings, then it's positive. Okay. So if we insert that equivalence into the equation for delta H, or the enthalpy, then we get delta H equals Q plus W plus any change in pressure volume. If the process takes place at constant pressure, then we can pull that pressure term outside the delta. So now pressure is outside and it's not, it's constant, doesn't change. Right? Now we know that work, and I think this may have been done in an earlier chapter, but it bears repeating. Work is an expression of pressure times a change in volume, but due to the convention again of when work is done by the system on its surroundings, then the work is leaving the system, so it's negative. But if we measure that in terms of pressure times volume of gas, then we get a positive value. So we have to introduce that negative sign in order to maintain the sign convention that we've adopted. Okay, now if we do that, if we insert that minus P delta V in for W, then we get overall, we get delta H equals the equivalent of Q, which is minus P delta V, and then the P delta V, let's see, I left out Q, excuse me. That's W. This is Q. Let's see. Yeah. Oh, okay. I left out the other one. Let me be complete. This is delta E plus P delta V. Okay, so now we're going to say that this delta E equals Q plus W. This is Q plus W. And now we're going to say that the equivalent of W is minus P delta V, right? So those are sequences of terms. And then we add the P delta V here. Notice that that one cancels that one. And in this case, a value for delta H is equal to Q. But it's only equal to Q when the pressure does not change. Okay, when pressure is constant, then a measured value of Q is equal to the enthalpy for the reaction. That's why scientists, when they conduct these types of experiments, will try to conduct the experiment, if they're going to measure any heat transfers and try to get at a term for enthalpy, then what they'll do is try to conduct the experiment under constant pressure. That way, any measurement of Q is equal to a change in enthalpy. All right. So let's go to okay. That erase is okay, but it's certainly a chore. Pardon me for just a minute. I want to condition this board. It won't take a second. All right. Now let's get back to chemistry. I'll preface the discussion here by reminding you that the authors of the textbook, when they say delta S universe, it's very likely that what they mean is the change in entropy for the total, that is, system plus surroundings. And in our model, we isolated the system and surroundings from the rest of the universe. So bearing that in mind, just do the conversion in your head. Delta S universe is delta S total. Okay. If using this formula, I think it's sent. Yeah, that's okay. Using this formula, delta S total, that's messing up. Delta S total equals delta S for the system plus delta S for the surroundings. Okay. So in order for a process to be spontaneous, the total, or in this case, the delta S for the universe, the delta S for the total should be positive. Right? Then we can say that the process is spontaneous. Well, if the system is increasing in entropy and the surroundings is increasing in entropy at the same time, then the total is going to be positive. So in that case, if system and surroundings are both positive, the delta S for total is also going to be positive, and that process is always spontaneous. And the flip side is, if this is negative, that's negative, then this has to be negative, and that's not positive in the forward direction. But in the reverse direction, it will be spontaneous. So in terms of a chemical reaction, if it's not spontaneous in the forward direction, just flip it around. It's spontaneous in the reverse direction. Now, in the situation where delta S system is positive and surroundings is negative, the only time that this value is going to be positive and the process will be spontaneous is if the magnitude of this term is larger than the magnitude of that term. That makes it positive. And vice versa, right? If this is negative and that's positive, by the same logic, the entropy change for the surroundings has to be more positive than the entropy change for the system is negative. In that case, it would also be spontaneous. But we don't know unless we actually have the values assigned to those terms. Okay. Now we're going to talk about a man by the name of Josiah Gibbs. He was an American, and he was working in the latter part of the 19th century. And he was interested in determining in a process, chemical or physical, it doesn't matter, in a thermodynamic process, how much of the energy that is derived from that system can be used to do useful work. In other words, it was common knowledge that in heat engines of the time, most often steam engines, that all of the energy that was expended in operating the engine was not converted into useful work. In fact, they were very, very inefficient. In the beginning, steam engines you were lucky to get 1% efficiency. So if you had 1,000 joules go through the process, you may get 10 joules of work out of it. Okay. So Gibbs wanted to
It was trying to determine how much of that work was theoretically possible, to how much of the energy was theoretically possible to extract as useful work. Okay? So he went. We won't go through the whole the whole story, but the short version is he came up with this expression. This is Gibbs free energy. Free refers to energy that's available to do work. This is the maximum amount of energy extracted from a process that can do useful work. Now, it may not be all converted to useful work, but this is the maximum. And if you know the enthalpy change for a process, right, then you have to subtract losses due to entropy. Okay, so that's Gibbs' equation. And we're referencing here the system. We're talking about the system, not the surroundings, just the system at this point. Because there are no subscripts, then we just assume that we're talking about the system. All right. So we're going to transform this equation a little bit and try to derive some more information from it. What you'll notice is these are energy terms, right? So this is going to be in joules. This is going to be in joules. This is going to be in K for temperature. That means this one has to be joules per K. Right? In order for the K to cancel, this has to be the same unit overall as this one. Right? So those are the units of measure. All right. Now we're going to transform this thing by, we're going to divide the whole equation through by a minus T. So minus T, minus T, minus T. Okay? That gets rid of this minus and that T and that T. So now we have plus delta S. And over here, we have minus delta H over T. And here we have delta G minus delta G over T. All right, we've just done some math. Okay, we know that the delta S for surroundings equals minus enthalpy over temperature. All right, so this term then becomes the entropy of the surroundings. And of course, this term, because it has no subscript, must be the entropy of the system. Right? So what is this equal to? From a previous slide, this is equal to delta S total. So that means that this term minus delta G over T equals delta S total. Okay? What does that say about the spontaneity of the process? That says if this is positive, the process is spontaneous. That means that if delta G is negative, then this term becomes positive. Right? So if delta G is negative, the process is spontaneous because a negative times a negative is positive. Okay? We have another way to determine spontaneity. If we determine the free energy of the process is negative, that means the process is spontaneous. All right. All right. So we also have to keep the temperature constant, right? Because if we let both of them vary, then the temperature could influence the outcome. So we're saying that both temperature and pressure are constant for the determination of this relationship. All right. So let's look at, well, that's not erasing as good as I thought it would. All right. So in this concept check, a liquid is vaporized at its boiling point, constant pressure. So we're going to predict the sign of each one of these terms. If a liquid is vaporized, we're going from some liquid to some gas. It's not a chemical change, right? We're just vaporizing a liquid. It's changing state. So if the liquid is the system, then is there any work being done? Well, as the liquid vaporizes, it expands its volume, correct? If it's at constant pressure, then we have to let the volume expand in order to maintain the Boyle's law relationship. So that means the vaporizing gas, the system is doing work on its surroundings. So that means W is negative, right? Should be. Gas does work on its surroundings, so it's negative. How about the heat? Heat has to go into the system from the surroundings. So Q should be positive. All right. How about delta H? Well, if we're in a situation of constant pressure, then Q and delta H are the same. So delta H is going to be positive also. Okay. How about the delta S of the system? Well, if the system is expanding, it's creating more microstates. So the delta S for the system is positive, more disordered. So the delta S, and I won't write system here because it's understood. If you don't put a subscript, then you're talking about the system. Well, how about the delta S for the surroundings? Well, if heat is being extracted from the surroundings, then the delta S for the surroundings should be negative. All right. So the delta S for the surroundings is negative. How about delta G? Is the process spontaneous? At the boiling point, which is where we're at, constant pressure, and we're just changing phase, right? That means the temperature is constant. Delta G, at equilibrium, delta G is 0, right? There's no Gibbs energy change at all at equilibrium. So delta G is 0. Not positive or negative. Okay, so if we say that delta G equals delta H minus T delta S, and this is 0 and equal to these terms, then we can solve. We just move this one over the other side and makes it positive. Delta H equals T delta S. at equilibrium. Right? We could solve this for other terms, right? We could say delta S for the system. So delta S for the system then is equal to delta H over T. And that's positive. Okay? At equilibrium. So all we had to do was change the sign from our previous formula. Delta S for the surroundings is minus delta H over T. But at equilibrium, delta S for the system is positive delta H divided by T. Okay. The value of delta H for vaporization of a substance is 45.7 kilojoules per mole, and its normal boiling point is 72.5 degrees C. Calculate the delta S for the system, delta S for the surroundings, and delta G for the vaporization of 1 mole of this substance at 72.5. So if we're vaporizing it, that means delta G has to be 0, right? At equilibrium, the free energy is 0. Okay? We know that the surroundings then is minus delta H over T, and by convention, delta S is in terms of joules, joules per K. Oops, sorry. Joules per K, and this is per mole also. So we have to convert kilojoules to joules, right? We can't compare apples and oranges. So it all has to be converted to joules, and that's why we have 45.7 times 10 to the third. And then we have to convert the temperature to K, so we do that, and we multiply those together, and we get minus 132 joules per K mole is the delta S for the surroundings. And since we're at equilibrium, then the delta S for the system is just equal to the sign change for that value.
Professor Dave here. Let's learn the laws of thermodynamics.
He knows a lot about the science stuff. Professor Dave explains.
The laws of thermodynamics help us understand why energy flows in certain directions and in certain ways. A lot of the concepts described by thermodynamics seem like common sense, but there is a layer of math beneath the intuitive level that makes them very powerful at describing systems and making predictions. We won't get into the math, but we should be able to describe these laws conceptually. The first law, described in the most basic way, highlights conservation of energy. Energy is not created or destroyed, it only changes forms, from potential energy to kinetic energy to heat energy, etc. While we have found this to be untrue on the quantum level, for chemists it does just fine. However, there seems to be a preferred direction in which energy flows from one form to another. In order to understand why, we look at the second law. The second law introduces a new concept, entropy. Entropy is quite difficult to understand, but we can most easily describe entropy as disorder. And the second law states that the sum of the entropies of a system and its surroundings must always increase. In other words, the entropy or the disorder of the universe is always increasing. Within a system, there is also a tendency to go towards higher entropy. The classic analogy is that your bedroom will over time become messy, but it won't suddenly become neat. Another way to look at this is to say that entropy is a measure of how dispersed the energy of the system is amongst the ways that system can contain energy. Yet another way is to analogize entropic states to computer code. Let's take, for example, an ionic solid compared to the same substance as a liquid. Clearly, the solid state is more ordered and the liquid state is more disordered or higher in entropy. To describe the solid state using computer code, you would need to include terms that describe the geometry of the lattice, the intermolecular distances, the precise configuration of every molecule, and many other things. But to describe the liquid state, you would need to simply describe the volume of liquid and the shape of the vessel, because the motion and configuration of the molecules are random. That's far less information that needs encoding, which is a way of rationalizing why increasing the entropy of a system is thermodynamically favorable. We can look at all kinds of processes to highlight entropic influence. Heat will flow from a hot coffee cup into the table or your hand because the heat energy will be more disordered if more dispersed. This is why heat spontaneously flows from hot to cold and not the other way around. Entropy. The third law states that a perfectly crystalline solid at absolute zero has an entropy of zero, as this is the most ordered state the substance can be in. Entropy is measured in joules per Kelvin. Note that entropy is not a measure of energy itself, but of how energy is distributed within a system. It is enthalpy, the thermodynamic quantity we learned about before, that is more accurately describing the energy of a system. As we will see, enthalpy and entropy intricately relate to tell us something about the Gibbs free energy of a system. G, or Gibbs free energy, tells us whether a process will be spontaneous or not, meaning if it will simply happen on its own. Change in Gibbs free energy is given by this equation, which includes change in enthalpy, change in entropy, and temperature. If delta G is negative, the process is spontaneous. If positive, it is non-spontaneous. So we can use this equation to see how a spontaneous process can be either enthalpically or entropically favorable, or both, but not neither. For example, if delta H is negative, which means exothermic and energetically favorable, and delta S is positive, which means an increase in entropy, which is also favorable, a negative minus a positive will always be negative, or spontaneous. If the opposite is true, and both are unfavorable, we have a positive minus a negative, which will always be positive, or non-spontaneous. If only one of the two is favorable, we have to do some math. If delta H is positive or endothermic, that energetic unfavorability could be outweighed by the other term if the process is entropically favorable. And since T is here, this factor will increase with a larger T, so entropically favorable processes are more likely to be spontaneous at higher temperatures. Conversely, if it is energetically favorable but entropically unfavorable, the entropic unfavorability will be minimized at lower temperatures. This is a very important equation to understand, because it describes all of the spontaneous processes in the universe. There are those who incorrectly use entropy and the second law of thermodynamics to imply that order can't happen spontaneously. But we just showed that entropically unfavorable processes can be spontaneous at lower temperatures if they are energetically favorable. An example of this is soap. You need soap to wash non-polar dirt and grime off your hands because they are immiscible with polar water molecules. But soap molecules have polar heads and long non-polar tails, which allows them to spontaneously form structures called micelles. These are spheres where the soap molecules orient themselves with the polar heads facing out in order to maximize ion-dipole interactions with water molecules that bring the system to a lower energy. And the non-polar tails will all face in, trapping the dirt by making a network of van der Waals interactions. The dirt trapped in the micelles washes away because the micelle as a whole is water-soluble due to the polar heads facing out. That's how soap works. And that's also how highly ordered structures can form spontaneously if by enthalpically favorable or energy-storing processes. In this way, systems can defy entropy on the small scale, but the second law does hold true in that the entropy of the universe is always increasing. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
So one of the discussion points for Professor Dave was the Gibbs free energy equation and predicting spontaneity under different conditions, of which the enthalpy is positive or negative and the entropy is positive or negative. So for this equation, if we have a positive value here and a negative value here, then this is only spontaneous at high temperatures. Excuse me. We want a negative here to be spontaneous. Okay. Oh, so it's spontaneous no matter what the temperature is. This is always negative because of that sign. If we have both are positive, we want this to be negative, then the T must be very high. So at high temperatures, this is negative at high T, because that makes this term big enough to overwhelm that term. On the other hand, if we have both negative, then we want to minimize this term because that makes it positive. So this is negative only at low temperature. Okay. And the last one where this is negative and this one's positive, then this is never negative. It's never spontaneous at any temperature. Okay. I hesitate to go over this slide because it's always given us trouble in the past. I don't know if it's going to help any. Let me see what else is coming and if we'd be better off spending our time. Yeah, I do have 2 slides, so maybe. Okay. We'll take a look at it. Oh, by the way, remember when we were calculating the enthalpy of a reaction based upon the summations of the enthalpies of the individual bonds? And those that were the enthalpies of elements in their standard state, like this one, had an enthalpy of 0. Okay, that's our anchor point to elementals. Well, for entropies, for entropy terms, they are never 0. You always have an entropy term for everything, elements, compounds, whatever. Because the only time you have delta S at 0 is at absolute 0 for a perfect crystal of that compound or element. Okay, that's the 3rd law of thermodynamics. So we always have a value for entropy. Okay, so let's say we have, let's put this information up here that we were given. Gas A2 reacts with gas B2 to give gas AB. So this one is a gas, and this one is a gas, to yield AB. Right. So we have to have 2 there to balance it. And let's see, I got something in the way here. At constant temperature and pressure. Constant temperature and pressure. Okay. The bond energy of AB is much greater than that of either reactant. So the, let's see, how do I write that? The, delta H for AB is greater than either of the reactants. Is greater than this one, delta H for B, or delta H for A. So what do we mean by bond energies? The way bond energies are determined is how much energy does it take, positive value, do we have to put into that to break that bond? So bond energies are always going to be positive values. Okay. So predict the signs of delta H, delta S surrounding system in total. All right, so I already said that for terminology, yes. Energy required to break the AB is greater than AA or BB. More energy must be supplied to break AB, and it is at a lower energy state than either AA or BB. There we go. Oh, so this was the enthalpy. I think that we did this in the first semester. Enthalpy change for a reaction, if we take the energy required to break the bonds and subtract the energy released when the bonds reform for the products, then we can get a delta H. And the reason we have broken bonds or reactants first is because of the convention that they're always positive values. Okay. So the energy of the reactants is greater than the energy of the products, correct? Is that true? Yes. Okay, here's why. The energy of the reactants is greater than the energy of the products. So this is an exothermic reaction. The reason I can say that is I know that it takes more energy to break that bond than it does either of these. That means that this is more stable. It is at a lower energy state. So we have to add more energy into it to break the bonds. So that means the energy of the products has to be at a lower value than the energy of the reactants. Okay. So this makes it exothermic. Delta H is negative. All right. How about, let's see, which one are we going to do next? If we know that delta H is negative and delta S for the surroundings is equal to negative delta H over T, and this is negative, then this value is going to be positive. Okay, because this is negative, negative times negative is positive. Okay, we got that far. Delta S for the system, we don't know for sure if the delta S for the system is, we assume it's approximately 0, but we don't know for sure.
be less than 0. So the total then would be this one plus the 0, which would make it positive. So delta S for the total is positive. Now, the real sticking point here is delta S for the system. We can't determine that with the information that's given. All right. So there's your third law of thermodynamics again. And then here's a discussion of the standard entropies. We had standard enthalpies in a previous discussion. And these values are given at 1 atmosphere pressure and 25 degrees Celsius. So 25 plus 273 is 298 K. Okay. So what we're saying is that the delta S is always, there's always a value for the delta S's for every component in the reaction. So we take the delta S for the products and subtract the delta S for the reactants, since they're always positive. So the delta S, as a general rule, it's not absolute, but generally, the delta S, the standard delta S increases as the complexity of the molecule increases. So if we just look at the energy possibilities, the energy entropy, and we take water, well, that first one, you can have both hydrogens in their bonds are stretching, going back and forth like that together, or the molecules bending like this, or they're alternating stretch and compress, or the whole molecule can spin. Those are possibilities for this energy entropy for the water molecule. Whereas the diatomic hydrogen molecule can only do two things. It can either stretch or spin. So the more complex molecule has more possible states than the simpler one, the diatomic hydrogen. That's just an illustration of that general rule. Okay, so if we want to calculate the delta S for the following reaction, we simply take the delta S for sodium hydroxide, multiply it by 2, because they're 2 moles, and add that to the hydrogen, and then subtract from that 2 times sodium and 2 times water. And if we do that, we get minus 11 joule per K. And notice that standard enthalpies are generally given in joules, not kilojoules. Whereas entropies and free energies, well, free energies can be joules also. But delta H's are usually kilojoules. So you have to watch out for the units of measure. Okay. We can also apply standard free energies, right? You can look into a reference manual and find standard free energies for the various components in your reaction and determine the free energy for that reaction. Just sum of the products minus the sum of the reactants. So let's see if we don't have to get this one exact because we're not given values, but say a stable diatomic molecule spontaneously forms from its atoms. So a stable diatomic molecule, which would be, let's say, AA, spontaneously forms from its atoms. And to simplify it further, let's make that all gas. Okay.
So what are the signs of the delta H, delta S, and delta G? Well, the key there is spontaneous. If it says spontaneous, that means delta G0 is negative, right? How about delta S? Well, which is more ordered? This one, right? So if this one is more ordered than that one, then the delta S should be negative. It's going from higher entropy to lower entropy. So this one should also be negative. And then delta H 0. Let's see, do we have a, yeah, we do. Delta G0 equals delta H 0 minus T delta S. So if this one is negative and this one is negative, so for that one to be negative, well, we don't know the temperature, do we? Did it tell us the temperature? Didn't tell us the temperature. So let's see if we can reason this one out. This would be positive. In order to make that one negative, this one have to be negative. Yeah, that one would have to be negative. So it seems that they're all negative. Yep. So delta G0 is spontaneous, so it's negative. 2 to 1 is a negative entropy. And I use this explanation, but that explanation works also because the molecule at lower energy than separate atoms. We're saying that it's more stable over here. The energy yeah, these two have come together, and when you get two atoms come together, they always give up energy. Right? We know that from lattice energies. Okay, let's see. Are we getting close? Oh, we do have some tricky discussions coming up. As if they haven't been tricky enough already. So consider the following system at equilibrium at 25 degrees C. PCl3. This is a gas plus chlorine gas is in equilibrium with PCl5 gas. And delta G0 equals minus 92.50 kilojoules. Okay, it's important to remember that when we're talking about this 0, that's the standard conditions, 1 atmosphere pressure, 25 degrees C. And a delta G can be negative under those conditions, but if we change the conditions, maybe it becomes positive, right? If we change the temperature, change the pressure, then it could become positive. So that's always a possibility. So what will happen to the ratio of partial pressures of PCl5 to PCl3 if the temperature is raised? See if we got an explanation here. Okay, there's our Gibbs free energy. So delta S is unfavorable. Right? Delta S is negative, right? Because we're going from 2 of these molecules to this one. Going from 2 moles to 1 mole. But the reaction is system reaction. I'm not sure that we can say the reaction is spontaneous. Yeah, well, oh yeah, we can. Delta G is negative. All right, the reaction is spontaneous. So delta G is negative under these conditions. Okay. delta H must be negative, exothermic. Right, if this one, delta G 0 equals delta H 0 minus T delta S 0. If this one's negative and this one's negative, and in order for this one to be negative, that gives us a positive. This one must be negative, exothermic. Okay. What should happen to the ratio between the two? The ratio of PCl5, PCl 5 to PCl 3. Well, if it's spontaneous, did I put them in the right order? PCl 5 to PCl 3. If the temperature is raised, okay. If the temperature is raised, if this gets higher, if we increase the temperature, then this negative gets bigger, right? The negative, this term becomes, let's see, negative temperature. This becomes more positive, which means that the overall term becomes less negative or even positive. So that drives the reaction back this direction, which decreases this value and increases this value. So this ratio should decrease as T increases. Okay. I hope that makes sense. Yeah, we're invoking Le Chatelier. Now that was one explanation for it. The other is to use Le Chatelier and say, if this is exothermic, then the delta H is over here. And the delta H refers to temperature change. If we increase the temperature, we're adding energy on this side, drives it back the other direction. So that's a little more intuitive, I think, than looking at it from the enthalpy side or Gibbs free energy side. Okay. So let's see what relationship pressure and concentration have to do with our spontaneity of the reaction. I think we're at WD-40 is wearing off. Pretty good for a while. Okay, so here's the relationship. Remember I said that delta G under certain conditions, all right, under standard conditions, can be spontaneous. But delta G under the real conditions, like we change the temperature, we change the pressure, under real conditions, the delta G can flip to non-spontaneous. And these are the reactions that are giving this that relationship. The actual delta G for a reaction would be the delta G0 plus any change in pressure related this way. See, that's R. And natural log of pressure. So if this pressure is in atmospheres, that means this one must be liter atmospheres per mole K in order to, no, that doesn't make any sense. We'll come back to that. Since we're talking energy, it must be the 8.3145. Yeah, because the natural log of P, what does pressure need to be in? It must be atmospheres. But the R is in joules per K mole because this term is joules. Yeah. So it would have to be the 8.3145. And also, if the concentration changes, right? If we're at a non-equilibrium state, right, then delta G is no longer zero, right? This will be a value no matter what. But delta G will be zero if we're at equilibrium, right? If this is K, then that will be zero. But if it's Q, not equal to K, then this will be a value. All right. I guess we're going to digress for a moment. We're trying to make sense of what delta G means in a chemical reaction. We define it as free energy. So if we're headed for equilibrium, what does equilibrium mean? Equilibrium is not necessarily, well, actually, equilibrium is not a reaction that goes to completion. Equilibrium is where you have reactants to products can also go from products to reactants. So during a phase change, you're taking say a liquid to a gas, right? And it's not coming back. So that's what that one on the left is trying to illustrate. That ball rolls down to B and that reaction is complete. Whereas for chemical reactions that are at equilibrium state, the products might be B and the reactants might be A, and there's a happy medium in there somewhere at C. So at that C, where you have, I don't know if we want to equate that to energy, but at that point, you've got a situation where you're getting forward and reverse reactions balancing one another. So we already described the equilibrium state for delta G as zero. So if we set this equation, this equal to zero here, that means, or here, let's see, which one are they using? They're using this one. So if we're at equilibrium, that means this has to be K. Okay. So if we solve this for delta G, right, keep delta G here and put this on the other side, that means delta G zero then is equal to negative RT log K. So if we know the equilibrium constant for a reaction, and we know the temperature at which it occurs, then we can calculate the standard Gibbs free energy for that reaction. Or if we determine the delta G for a reaction, then we can, at a given temperature, then we can calculate K. So there we have an interchange between, and this is, yeah, zero. We have an interchange of information there. You can go either way. It gives us another way to determine K. Rather than having to measure the actual concentrations of reactants and products at equilibrium, then all we need to do is determine what is the delta G, zero, under those standard conditions. And T then, actually, we would select T at 25 or 298 K, because that's standard conditions. And this is 8.3145 times that, times that, times that, times log K. And whatever this value is, then we can solve for that unknown, determine what K is. All right, this is another one of those slides, and I'm not sure if it's going to be helpful. But let's take a look at it. I left it in here for a reason, so Let's see if it can help us understand processes. Let's see, how many slides? I got 2 slides in this set. So if we look at the Gibbs free energy for this, for a reaction of A going to B. And we express those energies in terms of what's the fraction of A reacted, or the which naturally tells us what B is. So we really only need to concentrate on A. So if we say the actual Gibbs free energy of A for this reaction can be written down as, since they're all gases, then we can say what's the standard Gibbs free energy for A plus RT times the natural log of the pressure of A. So the partial pressure of A is going to decrease over time. And we can write the same thing for B, because B is going to increase as A decreases. Then we can write a similar expression for B. Well, the total Gibbs free energy would be of whatever A happens to have and whatever B happens to have at any one point in that reaction. All right, that sets the stage for our further discussion. So as A disappears, then the Gibbs free energy for A decreases. And that's what we're seeing there on the left. The Gibbs free energy for A decreases, since the pressure of A is decreasing also. And as B appears, then the Gibbs free energy for B increases, since the partial pressure of B is increasing. Okay, so far so good. So as long as the Gibbs free energy of B is less than that for A, the reaction will proceed to the right. It will only stop moving. It will only reach equilibrium when the Gibbs free energy for B is equal to that of A. So again, the total Gibbs free energy is whatever A plus B at any one point in that graph. And the change in Gibbs free energy is products minus reactants, which has to be 0. That's equilibrium. And we find the equilibrium point it's different for each reaction, but in this case, it happens at about 0.75 fraction of A. I don't know how helpful that was. So let's see what we can determine if we use delta G0 equals minus RT log K. Use that reaction for the equilibrium situation. We know that if delta G is 0, right? If this is 0, what will give us on this side is 0? Well, we know that the standard temperature is a positive value and the R is a positive value times that negative. So the only thing that will give us 0 over here is if this term is also 0, right? So what will give us that term? Well, the base here is E, right? Oh, okay. All right. So if this is 0, then E to the what power equals K? This whole term has to be 0, but K is something. So if this is 0, then the natural log of K, what if K were 1? Then E to the 0 equals 1, right? Anything to the 0 power is 1. So if K were 1, then we get a 0 out of that term. because that's the power of E. So that means at equilibrium, well, if delta G 0 equals 0, then K has to be equal to 1. Right? We're only saying that if delta G actual equals 0, that's equilibrium. But if we're actually looking at this value for the standard conditions, then if that's 0, then K has to be equal to 1. This could be something else. Okay. So if delta G is less than 0, or let's look at it the other way. If K is greater than 1, right? If this is greater than 1, what does that do? Well, now with greater than 1, then we have to have a value here. Right? There must be a value here. So that means delta G has to be negative. Delta G0 would be negative then. If, let's see, if K is 1, then we get delta G0. If K is greater than 1, then we get a negative delta G. And greater than 1 Ks will give us a spontaneous standard Gibbs free energy. But if it's less than 1, then we go the other direction. We get a negative value for this term, and that gives us a positive for delta G. We're just trying to develop a sense of what happens under various conditions. Okay. Now, let's go back to the original definition of Gibbs free energy. Gibbs free energy is actually an expression for the maximum useful work that can be obtained from a process, physical or chemical. So what we're saying is, if we know what delta G happens to be at any temperature, under any conditions, right, we're not standard anymore, then if delta G is that free energy, then we should be able to get some work out of it. But this is the maximum amount of work. We haven't taken into account any inefficiencies in the system, or the machine, or any waste that might occur. Right? That's the maximum. This is like the pie in the sky. But from a purely theoretical standpoint, this only happens with a perfectly reversible process. This has to be a reversible process. So what we're saying is that the, let's see. It depends on the reaction. The changes that get you from one position to the other and give you this free energy have to be infinitesimally small. In other words, and that's a term in calculus called limits. You have to have the limits. You reach this by knowing the limit of the expression. So we're not going to go into that. But the process is only this efficient if it's reversible. Most processes, all real processes, are irreversible. So what that says is that delta max is only theoretical. You'll never get there. You might be able to get high values close to it, but you'll never get there. Okay. So let's take a quick look at the temperature dependence of K. And let's say delta G equals delta G 0 plus RT log K. I think that's right. Is that a plus? Yeah. If we're at equilibrium, if we're at equilibrium, then this value goes to 0. Okay, and now we have that familiar equation where we have delta G 0 equals negative RT log K. Okay. Well, delta G 0 can also be expressed as delta H 0 minus T delta S 0. We know that value. This is Gibbs' free energy equation under standard conditions. So if we divide the equation through by minus RT, right, minus RT, let's see, we're going all the way across. Yes. Minus RT and minus RT. Then we get an expression for, let's see, that cancels that. And this makes minus delta G 0 over RT equals log K, right? Equals minus delta H 0 over RT plus T's cancel, delta S over R, correct? See if I did that right. That one's right. That one canceled. That one's right. Minus out here over RT, and this is those negatives cancel, and we get delta S 0 over R. Okay. So this equation right here looks like a straight line. Y equals M X plus B. So there's the y-intercept of the line. Here's the, what's the X? Well, the M should be the constant part. So if we drag it out here, minus delta H 0 over R times 1 over T. And this is plus delta S 0 over R. And this is log K. So if we plot on the x-axis 1 over T and on the y-axis log K, right, we should get a straight line with a negative slope. So this would be log K, and this would be 1 over T, and the T has to be in K. Right, and we should get a negative slope. And the slope then would be equal to negative delta H 0 over R. And the y-intercept right here would be delta S 0 over R. So what we have to do is conduct this experiment at different temperatures and determine the K, and then we can plot it. Right, and there's your example. Right, those blue dots are real numbers, and the line is best fit. And from a statistical standpoint, R squared, do you know what R squared is? Okay. R squared over 0.9 is pretty good. All right. There we go. There are some problems in the review document that take you through actual working those types of equations. Okay, let's see. Achieving the maximum work available from a spontaneous process only occurs in a hypothetical pathway, right? That is reversible reversible processes. And since no processes are perfectly reversible, then all real processes never make it to maximum work. So you're going to lose some of that free energy to waste, some type of waste. Here we go. All right. So in conclusion, I'll close with a word expression for the first law. The first law, remember, is delta AE for the universe is always 0. And in English, that means you can't win. You can only break even, right? You can't get more energy out of a system than you put in, right? Then the second law comes along. It says you can't even break even. Okay. Any transfer of energy will result in some waste of the energy unless a temperature of absolute 0 can be achieved. If you can couple a process to absolute 0, then you can get maximum energy available out of that system. But we can't do that. Absolute 0, we haven't even found absolute 0 in the universe. So first law says you can't win, you can only break even. Second law says you can't even break even. And the third law says you can't get out of the game because you can never achieve absolute 0. It's a hypothetical value. So the long and the short is, whenever we use energy to do work, we degrade its usefulness. And the only way to get more work out of it is to devise a different process that allows us to extract more of that free energy. Now you can get processes to run in reverse. The way you do it is you couple a more spontaneous process in one direction with a process that's not spontaneous in the direction you want to go. Then you can force it that way. Perfect example of that is air conditioning. Right? Normally, your cool house will get warm because energy would be transferred into your house, but we want to get rid of it. So we couple the system in our house with a process such as the evaporation of a fluorohydrocarbon. That evaporation is spontaneous, and when it happens, it extracts energy from its surroundings. And those surroundings happen to be the inside of our house. So when you couple a more spontaneous with a non-spontaneous, you can get an overall process that is spontaneous and goes against the grain, so to speak. All right. So I'm going to stop that. Any questions?
The next week we're not doing.
No, we're not doing that lab. Let me show the peanut gallery what that lab looks like. Here's the lab we're going to do. Not next week. We're changing it to the week after. So it'll be on the same day that we actually cover this information. And this is an informal report. So that just means you sign and date it and you fill out the information and answer the questions on the document. So that way, you can finish it on that day and turn it in on that day and to be done with it. The other documents I gave out today were the slides set, of course, and I gave out both version 1 and version 2 of the review document. Because when we do the review next week, I'm going to be pulling problems from both of them. Okay. And then there's one crossword puzzle for this chapter. Okay. Okay, if there are no questions or comments, then we're done for the day, and we'll do a review on this topic next week. Let's see. Yes. I think I put the lab in there because we were having a review, and normally I put labs on review day, but it's not going to make any sense to you on that day because we haven't covered electrochemistry. So that's why we're going to try to squeeze it in if we can on the last day of regular class, and then the following week is finals, and that's when we'll have the exam on just the last chapter in electrochemistry. And as a reminder, the review is, you'll see a video in the Brightspace on the review for electrochemistry. We'll have to treat it that way. Okay. Well, we're done.